You fired one particle, one, at a wall with two holes. It went through both at the same time. A single photon, smaller than anything you can see, and it split itself in two, traveled both paths, and then landed like a ghost wave on the other side. Physicists have repeated this for over 100 years. The result never changes. And the stranger part? The moment you try to catch it in the act, it stops, like it knows. We're going to trace every layer of this mystery. The man who started it, the moment particles became impossible, the machine that erases the past, and the 2023 experiment that blew the whole thing open again. If this messes with your head, like and subscribe. It should. Let's begin. The year is 1801. A British scientist named Thomas Young is standing in a dark room, holding a pair of scissors. He walks to the window. He cuts two tiny slits into the blind, just wide enough to let two thin beams of sunlight bleed through. He holds up a card to catch the light on the other side, and what he sees on that card will haunt physics for the next 200 years. Young was trying to settle a fight, a very old fight. For over a century, scientists had argued about what light actually was. Isaac Newton said light was made of tiny particles, like miniature cannonballs flying through the air. Other scientists said light was a wave, like ripples spreading across a still pond. Both sides had arguments. Both sides had evidence. Nobody could prove it either way. Young believed in waves. He designed the simplest test he could think of. If light were a wave, he reasoned, then splitting it into two beams and letting them cross each other should produce a specific pattern. Waves interfere with each other. When the peak of one wave meets the peak of another, they combine and get bigger. When the peak of one wave meets the trough of another, they cancel out and disappear. This creates a rhythm of bright spots and dark spots, called an interference pattern. He held his breath. The card showed stripes, bright, dark, bright, dark, dozens of them, fanning out across the surface in perfect alternating bands. The two beams of sunlight had crossed each other exactly the way two ripples cross on the surface of a pond. The pattern was precise, mathematical, impossible to fake. In that moment, Young thought he had won the argument. Light was a wave. Case closed. He published his results, explained the math, and expected the scientific world to move on. They did not move on. Some scientists refused to accept it. Newton had been dead for only 70 years, and his reputation was enormous. Accepting Young's result meant saying Newton was wrong. That was uncomfortable for a lot of people. Critics attacked Young personally. One review called his work worthless and accused him of wasting the public's time. But the stripes were real. Other scientists repeated the experiment. They got the same stripes every time. By the middle of the 1800s, the wave theory of light had quietly become the accepted answer. Young had won. He went back to other work. He helped crack the code of Egyptian hieroglyphics. He moved on. The scientific world moved on too, until someone asked a simple follow-up question that Young had never considered. What if you could send the light through just one tiny piece at a time? Young had used a full beam of sunlight, millions and millions of light particles, all traveling together. The interference pattern made sense if you imagined all those particles behaving like a crowd of waves. But what if you sent just one single particle through? One photon? No crowd, no group behavior, just a single point of light, alone, aimed at two holes. Would you still get the stripes? The answer to that question would take another 100 years to find. And when scientists finally got it, the room went quiet, because the stripes came back, and nobody could explain why a single particle, traveling alone, could interfere with itself. Before Young walked into that dark room, the dominant idea about light came straight from the most famous scientist who had ever lived. Isaac Newton believed light was made of particles. He called them corpuscles, tiny solid pieces flying in perfectly straight lines from a source to your eye. His evidence seemed strong. Light casts sharp shadows. Waves do not cast sharp shadows. Drop a rock into a pond, and the ripples bend around every obstacle they hit, spreading out in all directions. But light travels in straight lines. Point a flashlight at a wall, and you get a clean, hard-edged circle. No bending, no spreading. To Newton, that proved it. Particles, straight lines, simple. He also explained reflection this way. When you look in a mirror, the image is clean and precise. Newton said that was because solid particles bounce off surfaces like billiard balls bouncing off a bumper. Waves, he argued, would make a blurry mess. And Newton was not just any scientist. He had invented calculus. He had explained the orbits of planets. He had described gravity in terms that let engineers build bridges and cannons with perfect accuracy. When Isaac Newton said something was true, it carried a weight that most people did not want to argue with. So for most of the 1700s, light was officially made of particles. Textbooks said so. Universities taught it. Brilliant people accepted it. But there were cracks in the story. One problem was color. White light, when passed through a glass prism, splits into a full rainbow. Red, orange, yellow, green, blue, violet. All separated by angle, spreading out in a fan of color. Newton explained this by saying different colored particles had different sizes and masses, so the glass deflected them by different amounts. It worked mathematically, but it felt forced. Nobody liked the idea of a rainbow being caused by differently sized cannonballs. Another problem was something called diffraction. When light passed through a very narrow opening, it did not come out as a sharp beam. It spread, just slightly. The edges of the beam fanned outward in a soft blur. Particles flying in straight lines should not do that. Waves naturally do exactly that. Scientists who noticed these cracks stayed quiet. Newton's reputation made disagreement feel dangerous to a career. Then a Dutch physicist named Christiaan Huygens came along and proposed the wave model decades before Young, laying out the math carefully. He was ignored for most of his life. The establishment did not want to hear it. But nature does not care about reputations. By the time Young performed his experiment, the cracks in the particle theory were wide enough to see clearly. Diffraction was getting harder to explain away. Color was still a problem. And a few brave scientists had already started writing papers suggesting Newton might have been wrong about this one thing. Young's double-slit result was the final blow. Two beams, crossing, creating stripes. That pattern had one explanation and one explanation only: waves. The particle theory of light collapsed almost overnight. Scientists who had spent their careers defending Newton's corpuscle model quietly changed their papers and moved on without admitting it. Light was a wave. Everyone agreed, for about 50 years. Then a young man in a Swiss patent office read the data on something called the photoelectric effect and saw something nobody else had noticed. Something that would bring the particle back from the dead and make the whole argument infinitely stranger. Here is what makes Young's experiment so strange. He built it to prove one thing, and it accidentally broke something much deeper. Walk through it slowly. Young set up his apparatus in that dark room. One light source, one barrier, with two narrow slits cut into it. One screen on the other side to catch whatever came through. The question was simple. What shape does the light make when it lands on the screen? If light were made of particles, you would expect two bright bands directly behind the two slits. Particles travel in straight lines. They go through a hole, they hit the wall behind it. Two holes, two bands. Clean, obvious. But Young got something completely different. The light spread out after passing through each slit. Both spreading beams overlapped in the space between the slits and the screen, and where they overlapped, something happened. Some spots on the screen got twice as bright as expected. Other spots went completely dark. The result was a series of bright and dark stripes covering the entire screen, dozens of them, arranged in a perfect mathematical pattern. This was wave interference. When a peak from the left slit arrived at the same spot on the screen as a peak from the right slit, the two added together and made a bright band. When a peak from one slit arrived at the same spot as a trough from the other, They cancelled each other out and left a dark band. The math was exact. The stripes matched the predicted pattern of wave interference so perfectly that no other explanation fit. Young wrote it up and published it. He was pleased. He had answered the question. Light was a wave. He had shown it clearly. What Young did not realize was that he had built a trap. His experiment was so clean and so repeatable that physicists kept coming back to it for decades. Every time a new theory about light emerged, someone would run it through the double-slit setup to check, and the stripes always came back. The experiment became a kind of ultimate test. If your theory of light could not explain the stripes, your theory was wrong. Then in the early 20th century, quantum mechanics was born, and physicists started asking a new kind of question. Young had used a full beam of light, millions of photons all at once, all passing through together. The interference made intuitive sense if you thought of them as one big crowd of waves all mixing together. But what about one photon, a single particle of light, fired alone? Would it go through the left slit or the right slit? And would it still make a stripe? The question sat in the back of physics for years. The technology to fire single photons did not exist yet, so it remained theoretical until it did not. By the mid-20th century, detectors had become sensitive enough to catch individual photons. Scientists built the apparatus. They dialed everything down to one particle at a time. They fired a single photon at the barrier with the two slits. It hit the screen. They fired another, and another. Slowly, over hours, they watched the impact points pile up. At first, it looked random, dots scattered everywhere. But as more photons arrived, a shape began to form. The stripes, one particle at a time, alone, with nothing to interfere with, and the interference pattern still appeared. Young's test had just gotten 100 times stranger. Picture the surface of a still lake. You drop one stone in, and a perfect ring of ripples spreads out from the center. Now drop two stones at the same time, a few feet apart. Two sets of ripples spread out. They cross each other. Where the peak of one ripple meets the peak of another, the water rises higher than either ripple alone. Where the peak of one meets the trough of the other, they cancel out and the surface goes flat. You end up with a beautiful, chaotic-looking pattern of high points and flat zones spreading across the entire lake. That crossing pattern is interference, and it is the signature of waves. Now bring that image back to the double-slit setup. Young shines a beam of light at a barrier with two slits. Each slit acts like a new source of ripples. Two sets of waves spread out from the two openings and cross each other in the space between the barrier and the screen. Where they add together, a bright stripe forms. Where they cancel, a dark stripe forms. The screen fills with alternating bands, like the keys of a piano laid on their side. The pattern is mathematically predictable. You can calculate exactly where each bright stripe will appear based on the distance between the slits and the wavelength of the light. And every time scientists run the experiment, the stripes appear exactly where the math says they should. Here is why that matters so much. To get this pattern, light had to come through both slits at the same time. You can check this by covering one slit. The moment you block one of the openings, the stripes vanish. You get a single blob of light directly behind the open slit. Boring. Predictable. Exactly what particles would do. Uncover both slits. The stripes return instantly. The pattern only exists when both paths are open. That means the wave went through both holes simultaneously, spread out, crossed itself, and created the interference. A single source of light split itself in two. When physicists confirmed this worked with single photons, one at a time, the interference pattern took on a completely different meaning. Because with one photon traveling alone, there was no second photon to interfere with. The photon had to have gone through both slits by itself, one particle, two paths. At the same time, the stripes on the screen were not random. After thousands of individual photons had landed, their impact points lined up perfectly along the bright bands and completely avoided the dark bands. Each lone photon, somehow, knew not to land where the dark stripes would be. How did it know? How did a single particle, going through one slit, know what was happening at the other slit? The only explanation that fit was that the particle had not gone through one slit. It had traveled as a wave through both simultaneously, interfered with itself in the space between, and then collapsed into a single point only at the moment of impact. Before landing, it existed as a spread-out wave of probability. Every possible landing spot had a different chance of being chosen. The bright stripes were high probability zones. The dark stripes were zones where the math said the probability dropped to zero. A particle that was also a wave that collapsed into a particle, the same object, both things at once, until the moment it hit something solid. That idea alone would have been enough to rewrite physics. But the strangest part was still ahead. Just as the world had settled on light being a wave, a 26-year-old clerk working at a patent office in Bern, Switzerland, published a paper that tore the argument open again. Albert Einstein was not working on the double-slit experiment. He was trying to explain something that had puzzled physicists for years, a strange observation called the photoelectric effect. Here is what the photoelectric effect was. Scientists had discovered that when you shine light on certain metals, the metal releases electrons. The light knocks electrons loose from the surface, like marbles getting flicked off a table. That part was fine. The weird part was how it happened. If light were a wave, then a brighter, more intense wave should knock out more electrons and give them more energy. You would also expect that even very dim light, given enough time, could build up enough energy to eventually knock an electron free. Waves are continuous. They accumulate, but that is not what happened. When scientists dimmed the light below a certain frequency, no electrons came out at all. Zero. No matter how long they waited, no matter how bright they made the dim light. But when they switched to light of a higher frequency, even a very faint beam knocked out electrons immediately. A continuous wave cannot do that. Waves carry energy evenly, spread across the whole surface. They do not care about frequency in that specific all-or-nothing way. Einstein's solution was radical. He proposed that light did not spread out as a continuous wave at all. Instead, it traveled in discrete chunks of energy, individual packets, each one carrying a fixed amount of energy determined by its frequency. He called these packets quanta. We now call them photons. Each photon carried exactly one bundle of energy. If that bundle was large enough, it could kick an electron free. If the bundle was too small, no matter how many arrived, none could do the job. It was like trying to knock a boulder off a cliff with pebbles. 1,000 pebbles thrown slowly accomplish nothing. One boulder launched fast clears it instantly. Einstein won the Nobel Prize for this explanation. It was clean, it was powerful, it matched every experimental result perfectly. But it created a catastrophic problem. Young had proven that light behaves like a wave. Einstein had now proven that light travels like a particle. Both experiments were airtight. Both results were real, and they completely contradicted each other. Light could not be both a wave and a particle. That made no sense in classical physics. A tennis ball does not suddenly become a ripple in the air. And yet, that is exactly what the data said. Light acted like a wave when it passed through slits. Light acted like a particle when it hit a metal surface. The same substance, two completely opposite behaviors. Depending on what you asked it to do, physicists coined a phrase for this: wave-particle duality. It was a polite way of saying they had no idea what light actually was. The problem felt unsolvable. You could describe what light did. You could predict its behavior in any given experiment, but you could not say what it fundamentally was. Then someone realized that light was not the only thing behaving this way. Electrons, solid chunks of matter, were doing it too. And that made everything so much worse. The technology took decades to build. Firing a single photon at a target sounds simple. It is extraordinarily hard. By the mid-20th century, physicists had developed detectors sensitive enough to register the arrival of a lone photon. They had light sources precise enough to release photons one at a time, with enough separation that each one traveled alone, never overlapping with the next. They rebuilt the double-slit apparatus and ran the experiment at its most extreme setting. 1 photon, 2 slits, 1 screen. They fired the photon. It traveled through the apparatus. It hit the screen. A single dot appeared. Exactly what you would expect from a particle. 1 point of impact. Nothing special. They fired a second photon. Another dot. Somewhere slightly different on the screen. Third photon. Another dot. Random looking. For a long time, it just looked like noise. Dots scattered across the screen with no obvious pattern. If you had walked in at that point and looked at the screen, you would have said the experiment was producing exactly what particles should produce. Random individual hits, building up slowly, but the scientists kept going. Hundreds of photons, thousands, tens of thousands, each fired alone with a gap between them, each arriving and leaving its mark on the screen, 1 dot at a time. And then the pattern emerged. The dots were not random, they were clustering, forming stripes, bright regions where dots piled up densely, separated by dark regions where almost no dots had landed at all. The full interference pattern, built 1 photon at a time, assembled itself across the screen like a picture developing in slow motion. Each individual photon had arrived as a single point, a particle, a tiny dot. But over thousands of arrivals, the dots had arranged themselves into the unmistakable shape of wave interference. That single result shattered something fundamental. For an interference pattern to form, waves must go through both slits at the same time and cross each other. Each photon had traveled alone. There was no second photon present to create a second wave. The only explanation available was that each individual photon had somehow gone through both slits simultaneously, traveled as a wave through the space between the barrier and the screen, interfered with itself, calculated the probability of where to land, and only then collapsed into a single point, a particle interfering with itself. 1 object, 2 paths, both real, both taken, at the same time. Physicists called this superposition. The photon existed in a blurred, spread-out state, occupying multiple paths at once, until something forced it to choose a specific location. Before that moment of choice, both paths were equally real. This was not a malfunction. It was not an instrument error. The experiment was repeated in labs around the world, with photons, then with electrons, then with atoms. Every single time, the interference pattern appeared. Every single time, individual particles arriving one by one built up the same wave-shaped distribution. The most basic building blocks of the universe were behaving in a way that had no equivalent anywhere in daily human experience. A photon was not acting like a ball. A photon was not acting like a water ripple. It was acting like something the universe had never had a word for. But the strangest part of the experiment had not happened yet, because nobody had tried to catch the photon in the act, and when they did, everything changed. Before a photon hits the screen in the double-slit experiment, where is it? That question sounds simple. It has an answer that is genuinely hard to accept. Before the photon lands, it exists as a mathematical object called a wave function. The wave function is a description of all the places the photon could possibly be, each assigned a probability. The photon does not have a single hidden location that you just do not know about yet. The probabilities are not a measure of your ignorance. They are the actual physical reality of the photon in that moment. The photon exists across all those possible locations simultaneously, spread out, blurred, nowhere and everywhere at once, within the boundaries the math allows. Think of it this way. Imagine a coin spinning in the air. While it spins, it is heads and tails at the same time, in the sense that the outcome has not been decided yet. A spinning coin is not secretly heads underneath, just waiting for you to see it. The result is genuinely undecided until it lands. Now imagine that the coin is not just undecided. Imagine that it physically occupies both outcomes simultaneously, and only becomes one thing when something forces it to stop spinning. That is what a quantum particle does, except instead of heads or tails, the options are positions in space. For the double slit experiment, this means the photon genuinely travels through both slits at the same time. Each slit has a non-zero probability in the wave function. Both paths are real. Both exist. The photon is a spread-out wave of potential, passing through both openings, crossing itself in the middle, calculating interference, and then condensing into a single point the instant it makes contact with the screen. The screen acts like the landing surface for the coin. The moment of contact forces the photon to choose one location, one dot, one outcome. Gone. Physicists call this the collapse of the wave function. Before collapse, the photon is a wave spread across space. After collapse, it is a particle with one precise location. The collapse happens instantly, and it happens at the moment of contact with the detector or screen. Here is the part that most people resist. The photon did not have a location before it hit the screen. Asking where the photon was while it traveled is like asking which side the coin was on while it was still spinning. The question does not have an answer, because the answer did not exist yet. This runs completely against how we think about reality. A ball thrown across a room has a location at every single moment. You could, in principle, take a photograph and see exactly where it was. The photon has no equivalent. Its location is genuinely undefined until something interacts with it, and that becomes critical when you add a measuring device. Because if the photon's location is undefined and spread out, what happens when you place a detector directly at one of the slits to check which path it took? You are forcing it to have a location before it reaches the screen. The wave function collapses early, and the stripes disappear. The wave function is the central object of quantum mechanics. Everything else in the theory flows from it. Erwin Schrödinger wrote down the equation that describes how wave functions evolve over time. He did this in 1926, and the equation works with extraordinary accuracy. It predicts experimental results to a precision that makes it one of the most successful equations in the history of science. Physicists use it every day to design lasers, semiconductors, and medical scanners. But what the wave function actually is, physically, nobody fully agrees on. Here is what it does. For any quantum particle, whether a photon, an electron, or something larger, the wave function assigns a probability to every possible location that particle could be found at. The probabilities follow strict mathematical rules. They add up correctly. They evolve smoothly over time, according to Schrödinger's equation. They respond to forces and barriers exactly the way experiments show particles respond. The wave function is not a physical wave you could touch or measure directly. You never observe it. What you observe is the result of it collapsing into a single outcome. The wave function itself remains invisible, operating beneath every experiment. One of the critical features of the wave function is interference. Two probability clouds can overlap and interfere with each other, exactly the way two water waves interfere. Where they add together, the probability of finding the particle goes up. Where they cancel, the probability drops to zero. This is exactly why the dark stripes in the double slit experiment exist. The probability of the particle landing in those regions has been cancelled down to nothing by the overlapping wave functions from both slits. The dark stripes are zones of zero probability. The bright stripes are zones of maximum probability. The particle follows the math perfectly, every time, landing where the numbers say it should. Now here is the part that generates the most debate among physicists. When the wave function collapses, what exactly happens? Before collapse, the particle has a range of possible positions, all equally real in some sense. After collapse, it has exactly one position. That transition from many to one is called the measurement problem, and it remains one of the deepest unsolved puzzles in physics. Schrödinger himself found the idea disturbing. He constructed a famous thought experiment to highlight how strange it was. He imagined a cat sealed in a box with a tiny amount of radioactive material. If the material decays, A mechanism kills the cat. If it does not, the cat lives. The radioactive decay is governed by quantum probability. Before anyone opens the box, the wave function of the atom inside is in superposition, both decayed and not decayed at the same time, which means, by the logic of quantum mechanics, the cat is both alive and dead simultaneously until someone opens the box and observes. Schrödinger found this absurd. He presented it as a reductio ad absurdum, a way of showing that something must be wrong with the standard interpretation. But the math kept insisting it was correct. Experiments kept confirming the predictions. The absurdity kept being real, and the double-slit experiment sat at the center of all of it, because if you placed a detector at the slits to catch which path the photon took, you were forcing the wave function to collapse early. You were observing the particle before it had finished doing its quantum thing. What happened when you did that was even more disturbing than the stripes. If a single photon goes through both slits at once, you should be able to catch it doing that. At least, that is what physicists thought. They added a detector, a small device positioned right at the barrier, sensitive enough to register the passage of a photon without stopping it. The plan was to observe which slit each photon passed through, while still allowing it to continue to the screen, catch it in the act, record the path, and see if the interference pattern survived. The physics community was genuinely curious. If the photon truly went through both slits, the detector should trigger at both slits at the same time for a single photon. That alone would be remarkable. Scientists switched the detector on. They fired the photons, one at a time, just as before. The detector registered each photon at one slit or the other. Left slit, left, right, always one. Always a clear, definite answer. The photon behaved like a particle going through a single hole, making a choice, landing on one side. But then, the physicists looked at the screen. The interference pattern was gone, completely. No stripes. The photon impacts formed two blobs, one behind each slit, exactly as you would expect from a particle going through one hole at a time. The wave behavior had vanished. The photon had stopped interfering with itself. The dark and bright bands were replaced by two simple, boring clusters of dots. The detector had destroyed the pattern, and the disturbing part was the mechanism. The detector worked by interacting with the photon very slightly, just enough to gain information about its location. That tiny interaction, that small transfer of information, was enough to collapse the wave function, to force the photon to choose a single slit, to eliminate the superposition entirely. The act of measuring had physically changed what the photon did. This is called the observer effect, and it becomes one of the most philosophically explosive results in the history of science, because it says that reality at the quantum level is not independent of observation. The photon does not have a definite path until something detects it. The moment you gather information about which slit it used, the interference disappears. The moment you stop gathering that information, the interference returns. You can test this by turning the detector off without moving anything else. Same apparatus, same photons. Detector off, the stripes come back. Detector on, the stripes vanish, over and over. The only variable is whether information about the photon's path exists anywhere in the universe. Scientists tried to find a loophole. What if the detector was physically disturbing the photon in some mechanical way, bumping it off course and ruining the pattern? They designed gentler and gentler detectors. They found ways to gather path information that required vanishingly small physical interaction. It did not matter. As long as the which path information existed, the interference pattern died. Something about the mere existence of information, about the photon's path being knowable, was enough to collapse the quantum behavior. The photon was not being disturbed by the detector in any mechanical sense. The photon was responding to the fact of being known, and that raised a question so uncomfortable that physicists spent decades trying to avoid asking it directly. What if the particle knew it was being watched? The pattern dies the instant you look. That sentence sounds like a line from a horror movie. In quantum mechanics, it is just a fact. To understand why this disturbs physicists so deeply, you have to understand what the interference pattern represents. It is the result of probability. The wave function of the photon spreads through both slits, crosses itself, and creates regions of high and low probability on the screen. The bright stripes are places where the photon is likely to land. The dark stripes are places where the math says it cannot land because the two probability waves cancelled each other down to zero. For those cancellations to exist, both paths must be live possibilities. Both slits must be contributing to the wave function at the same time. The moment you determine which slit the photon used, you have eliminated one of those paths. You have collapsed the wave function to a single root. A single root cannot interfere with itself. A single root produces a blob, not stripes. But here is the part that has never been fully explained. The collapse happens at the level of information, not at the level of physical force. A traditional detector works by absorbing a tiny bit of energy from the photon or becoming entangled with it in some way. That interaction leaves a trace, a record. The universe now contains information about which slit the photon used. And the moment that information exists, the superposition ends. Scientists have tried every variation they can think of. They have built detectors that interact with the photon as gently as physically possible. They have set up experiments where the detector runs, but the recorded data is never looked at by any human. The pattern still dies. The information alone is enough. Whether a person reads the results or not seems to be irrelevant. What matters is whether the path information exists somewhere, encoded in any physical system, including a detector that no one ever turns on. The most extreme tests have shown that if you set up the experiment so that path information could theoretically be recorded, even if your specific detector fails to capture it, the pattern still degrades. The photon appears to respond not just to what was measured, but to what could have been measured. That behavior has no classical explanation. A ball rolling through a slot does not change its trajectory based on whether someone could theoretically observe it. Physical objects do not adjust their behavior based on the potential existence of information about them. Quantum particles do. The working explanation in mainstream physics comes from the Copenhagen interpretation, the framework developed by Niels Bohr and Werner Heisenberg in the late 1920s. Their position was essentially this: do not ask what the particle is doing when you are not looking. The question has no answer. A quantum particle does not exist in a definite state until it is measured. The wave function is a complete description of reality, and that reality is fundamentally probabilistic. There is no hidden layer underneath where the particle secretly has a position. Measurement creates reality. Observation selects an outcome from a cloud of possibilities. Before the measurement, the outcome simply does not exist. Most physicists were not comfortable with this, and at least one was openly furious about it. His name was Albert Einstein, and he spent the rest of his life trying to prove Bohr wrong. He failed. The phrase sounds unscientific. Particles do not have awareness. They do not know anything, and yet the experimental data keeps producing results that look exactly like that. Here is a setup that makes the situation sharper. Scientists designed an experiment where the detector was placed after the slits, not at them. The photon would pass through the barrier first, travel some distance, and only then encounter a device that could, if activated, tell researchers which slit the photon had used. When the device was off, the photon hit the screen and built up the usual interference pattern. When the device was on, the stripes vanished, even though the photon had already passed through the slits by the time any detection happened. The photon changed its behavior in the region of the slits, based on something that had not happened yet when it was at the slits. At least, that is one way to read the timing. Physicists are careful about this. The better way to say it is that the photon exists as a wave function across the entire path from the light source to the screen. The collapse of the wave function involves the whole system at once, not just the piece of space immediately around the particle at one moment. When the detector becomes part of the system, the entire wave function reconfigures, but the timing still looks strange from the outside, and it gets stranger. Researchers set up a configuration where the choice of whether to activate the detector was made randomly after each photon had already passed through the barrier. A random signal, generated by a separate process with no connection to the photon, decided at the last instant whether the detector would turn on or off for that shot. The results matched perfectly. When the random signal said detect, the stripes were absent for that photon. When the signal said do not detect, the interference pattern grew by one more dot in the correct bright stripe location. The photon, at the time it passed through the slits, had no way to know what the random signal would say. The signal had not been generated yet. The photon had already committed to its behavior in the slit region before the measurement decision existed. And still, the final pattern on the screen perfectly reflected what that future decision would be. This result convinced some physicists that something deeply weird was happening with time inside quantum mechanics. The photon's wave function was not just uncertain in space, it was, in some sense, extended through time. The future measurement was reaching back through the experiment and shaping what the photon appeared to do in the past. Others rejected this interpretation and argued for cleaner explanations involving the mathematics of wave functions without invoking time travel or backward causation. But the debate about what is really going on has never been settled, and it was about to get much more intense, because a physicist named John Wheeler had a thought experiment that pushed the timing question to its absolute breaking point. He wanted to know what would happen if you waited until the photon was almost at the screen to decide whether to measure it. The answer he got changed the conversation forever. When physicists say observation, they do not mean a person looking at something. This is one of the most misunderstood ideas in all of science. The word observation in quantum mechanics does not require a brain, a consciousness, or a living thing of any kind. It means a physical interaction that transfers information from a quantum system to some larger physical record. Anytime a particle interacts with another physical system in a way that leaves a permanent trace, that counts as observation. A photon bouncing off a detector counts. A photon leaving a mark on a photographic plate counts. An electron changing the spin of another particle counts. None of these require a person to be present. This distinction matters enormously for the double-slit experiment. The reason the interference pattern dies when the detector is on is not because a human being is paying attention. It dies because the detector is a physical device that becomes entangled with the photon. The photon's path information is encoded in the state of the detector. The path has become real in the sense that it can now, in principle, be retrieved. Scientists ran a controlled version of this to prove it. They set up a detector that automatically recorded which path data but fed the output directly into a machine that immediately destroyed the record without letting any humans see it. The pattern still vanished. The information existed in the detector for a fraction of a second, was then erased, but the collapse had already happened. Then they ran a version where the detector was physically present but configured in a way that made it impossible to extract which slit information from it, even in principle. The data was scrambled in a way that could never be decoded. The interference pattern returned. The determining factor was not the presence of the detector. The determining factor was whether usable path information could exist. When it could, the wave function collapsed. When it could not, the wave function survived, and the stripes appeared. This is called the complementarity principle, first stated by Niels Bohr. Wave behavior and particle behavior are mutually exclusive. A quantum system can show you one or the other, never both at the same time. If you extract which path information, you get particle behavior. If you leave the path ambiguous, you get wave behavior. You choose which face of the coin you see by how you set up your measurement. No human mind required. The universe enforces this rule automatically, at the level of physical information, regardless of whether anyone is watching. This is a relief to some people and deeply unsatisfying to others. If observation does not require consciousness, then the collapse of the wave function is just a mechanical process. Physics as usual, no mystery. But if that is true, then why does the wave function collapse at all? What is special about a detector interacting with a photon compared to a photon traveling through empty space? Why does one count as observation and the other does not? That question is the measurement problem, and it has no agreed answer. What it does have is a test, a very extreme test, one designed by a physicist who wanted to find out what would happen if you let the photon travel almost all the way to the screen before deciding whether to observe it. He called it the delayed choice experiment, and the result was something nobody was fully prepared for. John Wheeler was one of the most creative physicists of the 20th century. He worked with Einstein. He coined the term black hole. He spent decades thinking about the deepest questions in physics, and one question kept coming back to him: when does the photon decide what it is? Specifically, does the photon commit to a path through the slits before or after the measurement decision is made? The standard story says the photon passes through the slits, travels to the screen, and collapses into a dot when it hits. The detector, if present at the slits, collapses the wave function early, at the moment of passing through. If absent, the wave function stays spread out until impact. Wheeler wanted to delay the decision further. He proposed a version of the experiment where the choice of whether to measure the photon's path was made after the photon had already passed through the slits, was already traveling through the air on the other side, and was milliseconds away from hitting the screen. His thought experiment worked like this. A photon is fired at the double-slit barrier. It passes through. Now it is in the space between the barrier and the screen. At this point, someone flips a switch. If they install a detector in the photon's path, the which path information gets recorded. If they leave the detector out, the photon continues and hits the screen as a wave. The choice is made after the photon has already passed through the slits. According to classical thinking, it should be too late. The photon already committed to its behavior at the slits. You cannot change what it did there by flipping a switch here. Wheeler predicted that the experiment would show otherwise. He believed the photon had not committed to anything at the slits. The wave function stayed open until the measurement decision was finalized, no matter when that decision was made. His prediction was correct. When the detector was inserted after the photon passed the slits, the interference pattern vanished, as if the photon had gone through one slit all along. When the detector was absent, the stripes appeared, as if the photon had traveled as a wave through both. The timing of the decision did not matter. What mattered was the final configuration of the measurement, even though that configuration was chosen after the particle was already in flight. Wheeler described this as the universe looking back at itself. The present moment of measurement, he argued, participates in defining what happened in the past. The photon did not have a history until someone decided how to look at it. He extended the thought experiment to its most extreme version. He imagined a photon traveling from a distant quasar, billions of light years away, bent around a galaxy by gravity, arriving at Earth after a journey of billions of years. A physicist on Earth chooses whether to measure the photon's path. Wheeler proposed that this choice, made today, would retroactively influence which path the photon took on a journey that began before Earth existed. The universe, in his view, was not a fixed past being revealed. It was a past being chosen in the present. Most physicists today would not use those exact words. But nobody has found an experiment that proves Wheeler wrong. The delayed choice experiment was not just a thought experiment for long. Physicists built it. Several versions of the experiment were performed beginning in the 1980s, and the results matched Wheeler's predictions with extraordinary precision. The clearest and most convincing version came in 2007, when a team of French physicists ran the experiment using a specialized optical device that could switch between two different configurations faster than the light travel time across the apparatus. Here is how it worked. A single photon was fired at a beam splitter, a device that sends it down one of two possible paths. At the far end, a second device either recombined the two paths, allowing interference, or kept them separate, allowing which path detection. The crucial detail was that the decision of which configuration to use was made by a random number generator after the photon had already entered the apparatus and was already traveling. The photon had no way to know, at the moment it entered, which configuration it would encounter at the end. When the apparatus was set to allow interference, the photon behaved like a wave and produced the expected interference signature. When the apparatus was set to detect the path, the photon behaved like a particle and produced no interference. These two outcomes matched the theoretical predictions perfectly, and in both cases, the behavior corresponded to what was measured at the end, not what was set up at the beginning. The photon, already inside the apparatus, already committed to some behavior in the past moments of its journey, changed that behavior based on a decision that had not been made yet. The experiment showed that the photon did not have a definite history until the measurement at the end was finalized. The past, in this sense, remained open until the present forced it closed. This is not a comfortable result. The entire framework of classical physics assumes that events have a fixed history. What happened, happened. The present does not reach back and rewrite it. That assumption is baked into every machine ever built, every prediction ever made, every intuition about cause and effect. Quantum mechanics appears to violate it, at least at the scale of single particles. Physicists who accept the Copenhagen interpretation say this is fine, because wave functions are not physical objects in space. They are mathematical descriptions of probabilities. The photon never had a classical history to begin with. Asking what it was doing before the measurement is like asking what the score of a game was before anyone played it. But many physicists find that answer unsatisfying. If the photon was real enough to travel from a laser to a screen, it should have been doing something during that journey. Its behavior at the screen should not depend on a decision made after the journey was underway. And then the quantum eraser experiment arrived. And it made the question of past and present so much stranger, because scientists did not just delay the measurement, they erased it afterward, and the stripes came back. The quantum eraser experiment begins with a simple and uncomfortable idea. What if you could take back a measurement? You detect which slit a photon used. The wave pattern dies. Now you erase the detection data, destroy the record, make it impossible to ever know which slit the photon used. Does the wave pattern come back? The answer, in a carefully designed experiment, is yes. Here is how physicists built this. Instead of using a simple detector at the slits, they used a process called spontaneous parametric down conversion. When a photon passes through a special crystal, it can be split into two entangled photons. These two photons are connected in a precise way. Whatever you learn about one tells you something about the other. In the quantum eraser setup, one of the entangled photons, called the signal photon, is sent toward the double slit barrier and continues to the screen. The other entangled photon, called the idler photon, travels in a different direction toward a separate set of detectors. Because the two photons are entangled, measuring the idler photon can reveal which slit the signal photon passed through. That which path information destroys the signal photon's interference pattern, exactly as expected. But the idler photon travels to a branching path. At one branch, its which path information is preserved. At another branch, the which path information is scrambled and made permanently unreadable, effectively erased from the universe. When the idler photon lands at the erasing branch, something extraordinary happens. The corresponding signal photon, already hit the screen moments earlier, retroactively shows interference. When the physicists sort through the signal photon impacts and separate out only those whose partner idlers went to the erasing branch, the interference pattern reappears in the data. The signal photons that hit the screen before the erasure decision was made show interference in a way that depends on what happened to their partner photons afterward. The order of events, taken at face value, reads backward. The signal photon hits the screen. Later, the idler photon goes to the eraser. The erasure happens after the screen impact, and the screen impact shows interference that corresponds to that later erasure. Physicists are careful to point out that this does not allow information to travel backward in time. You cannot use this to send a message to the past. The interference pattern only appears when you sort through the data after both the signal and idler photon outcomes are known. You cannot see it emerging in real time. Without that sorting step, the signal photon data looks completely random, but the correlation is real. The entanglement between the two photons connects them across time in a way that makes it look, from one angle, as though the future is reaching back and influencing the past. John Wheeler would have recognized this immediately. The present measurement, he argued, participates in shaping what happened. The quantum eraser experiment, run in real labs with real photons, appears to confirm that the past is not fully fixed until every connected future measurement is complete. And if that is true about particles, it raises a question about everything. What does it mean for reality to have a past at all? There are three main answers physicists have proposed. They are all strange. One of them might be true, and they completely disagree with each other. Retrocausality is the idea that causes can run in reverse. A future event can influence a past one. In everyday life, this is absurd. You drop a glass and it breaks. The breaking happens after the dropping. The cause comes first. The effect comes second. That is the direction of time. That is the direction of everything. But the quantum eraser experiment and the delayed choice experiment before it produce results that look exactly like retrocausality. The measurement made at the end of the experiment appears to determine the behavior of the particle at the beginning. The future choice appears to shape the past path. A small group of physicists take this seriously as a real physical mechanism. They propose that quantum particles do not just spread their influence forward through time, they send influence backward as well. Along the same path they traveled, like an echo running upstream, the particle's wave function exists in both time directions simultaneously, and measurement at any point collapses it in both directions at once. This framework is called the two-state vector formalism, developed by Yakir Aharonov and colleagues over several decades. It is mathematically consistent, it reproduces every known experimental result, and it reframes the quantum eraser in a way that feels almost logical. The photons past and future are both part of one unified quantum description, and collapsing one collapses the other. Most physicists do not adopt this view. The mainstream position is that retrocausality is a misleading way to read the data. The quantum eraser, they argue, does not require any influence to travel backward. The correlations arise from entanglement. The two photons share a single quantum state that spans their entire journey. Measuring one updates your knowledge of the other, regardless of order. No signal travels backward. No cause runs in reverse. This explanation is technically accurate. The math works out without invoking retrocausality, but it does not resolve the discomfort. The correlation still exists. The future measurement still correlates with the past behavior. Whether you call that retrocausality or entanglement, something connects the two events across time in a way that has no classical equivalent. The deepest version of the problem is this. In classical physics, the past is fixed and the future is open. What happened is settled. What will happen is not yet determined. Quantum mechanics scrambles this picture. The wave function of a particle is genuinely open in both directions until a measurement collapses it. Past and future are symmetric in the underlying equations. Time's arrow is something that emerges from thermodynamics, from entropy and the behavior of large systems. But at the scale of individual particles, the equations of quantum mechanics run equally well forward or backward. Some physicists believe this symmetry is a deep clue about the structure of reality. Others believe it is a mathematical curiosity that does not correspond to anything physical. The argument has not been settled. What has been confirmed is that the connections between particles across time and space are real, are measurable, and do not fit inside the framework of classical cause and effect. The question of what they do fit inside is exactly where the three great interpretations of quantum mechanics part ways. And the first one, the one that most physicists were taught as the default answer, says something that sounds almost like magic. Copenhagen is a city in Denmark. In the late 1920s, it was also the location of the world's most intense debates about what quantum mechanics actually meant. Niels Bohr ran a physics institute there. Werner Heisenberg worked closely with him. Together, they hammered out what became the dominant framework for understanding quantum theory, a set of principles now called the Copenhagen interpretation. The core claim is radical. A quantum particle does not have definite properties until it is measured. Before measurement, the wave function describes all possible outcomes and their probabilities. Measurement selects one outcome and destroys the others. After measurement, the particle has a definite state. Before measurement, it genuinely does not. This is not a statement about human ignorance. Bohr was not saying that the particle secretly has a location and we just do not know it yet. He was saying there is no location to know. The particle exists in a superposition of all possible locations, and that superposition is the complete physical reality. There is nothing underneath it, no hidden layer, no secret position waiting to be found. Reality, in this view, is created by measurement. The act of observation does not reveal what was already there. It generates what is there. The universe is a vast ocean of quantum potentials, and every measurement is an act of selection, pulling one definite outcome out of an infinite spread of possibilities. Bohr pushed this idea hard. He believed that questions about what particles do between measurements were meaningless. Asking where the photon was before it hit the screen was like asking what color a dream is after you wake up. The question fails to connect to anything real. Heisenberg contributed the uncertainty principle, which reinforced the Copenhagen view from a different angle. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of your instruments. It is a fundamental feature of reality. Precision in one property destroys precision in the other, because measuring one disturbs the quantum state in a way that erases the other. For decades, Copenhagen was the only game in town. Most physicists learned it, accepted it, and moved on to calculating. They called this the shut up and calculate approach. The math works. The predictions match experiments. Stop asking what it means. But not everyone was satisfied. Einstein spent years arguing with Bohr. He believed quantum mechanics was incomplete. He believed particles did have definite properties before measurement, that there was a hidden reality behind the probabilities. He designed thought experiments to expose what he saw as flaws in the Copenhagen view. Bohr answered every one of them, and experimental results, decade after decade, confirmed the predictions of Copenhagen, not Einstein's classical intuitions. Einstein died in 1955, still convinced that quantum mechanics was missing something. The double slit experiment had become the arena for the deepest fight in physics. And just as Copenhagen seemed settled as the default view, a young physicist named Hugh Everett published an idea in 1957 that proposed something even more unsettling. He said the wave function never collapses at all. Hugh Everett was a graduate student at Princeton when he proposed his idea in 1957. His advisor was John Wheeler. The physics community mostly ignored him. He left academia, went to work for the Pentagon, and died at 51. Decades later, his idea became one of the most discussed theories in all of physics. Everett's starting point was simple. The wave function never collapses, ever. The Copenhagen interpretation says that when a measurement happens, the wave function collapses from many possibilities down to one definite outcome. Everett looked at that claim and asked a direct question. What is the physical mechanism? What actually causes the collapse? What changes in the universe at the moment of measurement to make all the other possibilities disappear? Nobody had an answer. Copenhagen just said it happened. It gave no deeper explanation. Everett proposed a different reading of the math. When a particle in superposition interacts with a detector, the superposition does not end. It spreads. The detector, the lab, the scientist, the air in the room, all of it becomes entangled with the particle's multiple possible states. The entire system enters a superposition. Every outcome that the wave function assigned a non-zero probability to actually occurs in a separate branch of the universal wave function. From inside one branch, you see one outcome. The electron hit the left side of the screen. The cat is alive. The detector clicked, and everything feels definite and classical and normal. But in other branches, other outcomes are equally real. The electron hit the right side. The cat is dead. The detector stayed silent. Those branches are inaccessible to you, but they exist. Every quantum event with more than one possible outcome splits the universe. A photon hitting a double-slit barrier does not go through one slit. It goes through both, and the universe divides into a version where it went left and a version where it went right, with an observer in each version who sees a single, definite result. This is called the many worlds interpretation, or sometimes the Everett interpretation. It sounds like science fiction, but the mathematics behind it is clean and rigorous. Everett was not speculating wildly. He was following the equations of quantum mechanics to their logical conclusion without adding any new assumptions. Copenhagen adds an extra rule, the collapse rule, on top of the standard equations. Everett removed that rule entirely and asked what you get. You get infinite parallel worlds. The appeal of many worlds to many physicists is precisely that it adds nothing. No special collapse mechanism. No measurement triggering a mysterious change in the wave function. Just the Schrödinger equation, running forward, branching endlessly. The problem is that the branches are undetectable. You can never observe a parallel branch. You can never communicate with another version of yourself. The theory makes the same predictions as Copenhagen for every experiment you can actually run, which means there is no test that distinguishes between them. Some physicists find this disqualifying. A theory that cannot be tested is not science, they argue. Others point out that the same charge applies to the idea of wave function collapse. Nobody has ever directly observed a wave function collapsing. That process is equally invisible, equally untestable in isolation. The debate comes down to which mathematical framework you find more natural. And then there is a third option, one that says both Copenhagen and Everett are wrong about the most basic assumption. One that says particles were never waves to begin with. What if the particle was always a particle? That is the starting point for pilot wave theory, also called Bohmian mechanics, developed by physicist David Bohm in 1952. Bohm looked at the double-slit experiment and proposed that the weirdness had a different explanation. The particle, he said, is always a solid object traveling along a single definite path. There is no superposition. There is no being in two places at once. The particle goes through exactly one slit, but it is not alone. Alongside every particle, Bohm proposed the existence of a real, physical wave field that fills all of space. He called it the pilot wave. This wave has no energy of its own. You cannot detect it directly. It does not push the particle physically. What it does is guide the particle's path, shaping the trajectory in a way that depends on the wave's interference pattern. The pilot wave travels through both slits simultaneously. On the other side of the barrier, it interferes with itself and creates a complex landscape of hills and valleys in the wave field. The particle, riding along this landscape, gets steered by the shape of the pilot wave. It follows a path that naturally avoids the regions where the pilot wave has cancelled out to zero. The result is that particles, over many runs of the experiment, accumulate in exactly the pattern of an interference distribution. Bright stripes in the regions where the pilot wave has peaks, dark stripes where it has zeros. Same experimental result, completely different mechanism. No superposition required, no collapse, no parallel worlds, just a particle and its invisible guiding wave. Pilot wave theory also explains the observer effect. When a detector is placed at one of the slits, it physically interacts with the pilot wave, disturbing its shape and destroying the interference pattern in the wave field. The particle then travels through a disrupted landscape with no interference structure and lands in one of two blobs instead of stripes. This explanation is entirely local and entirely classical in spirit. The particle always has a definite position. The wave always has a definite shape. There is no mysterious collapse, no branching universe, no reality created by observation. So, why do most physicists not accept it? Several reasons. First, pilot wave theory is difficult to extend to the full framework of quantum field theory, which describes particles at the deepest known level of physics. The original version works well for basic quantum mechanics, but runs into serious technical problems when you try to apply it to relativistic physics and particle creation and annihilation. Second, the pilot wave itself is strange. It fills all of space instantaneously. It is affected by every slit in the barrier, every detector in the lab, every configuration of the apparatus, regardless of distance. In this sense, it is non-local. Information about the entire experimental setup is built into the wave everywhere at once. This non-locality troubles physicists who want their theories to respect the speed of light as a limit. Third, and most fundamentally, the pilot wave cannot be measured. It guides particles but leaves no direct trace. This makes it feel, to some physicists, like a mathematical fiction rather than a physical thing. Pilot wave theory makes identical experimental predictions to standard quantum mechanics. Every test produces the same numbers. Like many worlds, it is empirically indistinguishable from Copenhagen. 3 interpretations, 3 completely different pictures of reality, 0 experimental tests that separate them. That situation has lasted for over 100 years. The double-slit experiment has been running in various forms since 1801. Quantum mechanics as a formal theory has existed since the 1920s. Every prediction it makes has been confirmed. It is the most accurately tested scientific theory in history, and physicists still cannot agree on what it means. The disagreement is not about the math. The equations are not in dispute. Every trained physicist uses the same formulas, gets the same numbers, and makes the same predictions. Experiments confirm those predictions consistently, often to more than 10 decimal places of accuracy. The disagreement is about interpretation, about what the math is telling us about the structure of reality, about whether the wave function is a real physical thing or just a calculation tool, about whether collapse actually happens or whether the universe branches, about whether particles have definite positions when nobody is looking. These are not questions you can resolve by doing another experiment. Every interpretation predicts the same experimental outcomes. The difference between them is entirely in what they say is happening underneath the data, at the level of physical reality itself. This is deeply unusual in the history of science. Normally, competing theories make different predictions, and you run the experiment to find out which one is right. That standard method does not work here. The interpretations are empirically equivalent. You cannot build an apparatus that returns a different number under Copenhagen versus many worlds. The number is always the same. Some physicists believe this means the question is unanswerable and therefore unscientific. They say physics should stick to predictions and calculations and leave metaphysical questions about reality to philosophers. This is essentially the spirit of the shut up and calculate approach that dominated the field for most of the 20th century. Others believe the question is urgently important. They argue that building a coherent picture of physical reality is the entire point of science. Getting the right numbers without understanding what those numbers are describing is not a complete theory, only a recipe. A minority of physicists are actively trying to find experimental cracks between the interpretations. Some proposals involve looking for subtle statistical deviations in quantum measurements that might favor one model over another. Others involve testing whether quantum superposition can exist in larger and larger objects, which could constrain the point at which classical behavior takes over from quantum behavior. None of these tests have produced a decisive result yet. What has happened is a steady expansion of the domain where quantum behavior has been confirmed. Physicists keep pushing the experiment to larger scales, and the quantum results keep holding. And that expansion has been producing results that stretch the strangeness further than anyone expected. Because the double-slit experiment was supposed to be a thing that only worked for tiny subatomic particles, something that would break down when you tried it with anything large enough to see. It did not break down. Louis de Broglie was a French physicist who had an idea in 1924, a bold one. Einstein had shown that light, which everyone assumed was a wave, also behaved like a particle. De Broglie asked the reverse question: what if particles, things like electrons that everyone assumed were solid, also behaved like waves? He worked out the math. He proposed that every particle in the universe has a wavelength. The formula tied the wavelength to the particle's momentum. Heavier, faster particles have shorter wavelengths. Lighter, slower particles have longer wavelengths. Electrons, being extremely light, should have wavelengths short enough to produce interference effects when passed through slits the right size apart. De Broglie submitted this as his doctoral thesis. His examiners were uncertain what to make of it. They sent a copy to Einstein. Einstein read it and called it impressive. The thesis was accepted. 3 years later, in 1927, two American physicists at Bell Labs, named Clinton Davison and Lester Germer, were bouncing electrons off a nickel crystal and accidentally discovered exactly the interference pattern de Broglie had predicted. They had not set out to test the wave theory. The discovery was a complete accident caused by a laboratory mishap that changed the crystal's surface structure. When they realized what they had found, physics changed overnight. In 1961, a German physicist named Klaus Jönsson built a proper double-slit apparatus for electrons and ran the experiment deliberately. The results were identical to Young's original light experiment. Individual electrons, fired one at a time at a barrier with two slits, built up an interference pattern on the screen, the same bright and dark stripes, the same mathematical spacing, the same dependence on the slit width and the electron's wavelength. Electrons, solid chunks of matter with mass and charge and measurable physical properties, were behaving exactly like waves when left alone to travel without being observed. And they responded to observation the same way photons did. Place a detector at the slits to record which opening each electron used, and the interference pattern vanished immediately, replaced by two blobs. Remove the detector, and the stripes returned. An electron passing through both slits at once, an electron interfering with itself, an electron changing its behavior based on whether path information existed in the universe. This was a different kind of shock than the photon result had been. Photons are particles of light. They are unusual. They travel at the speed of light and have no mass. You might tell yourself that photons are special, that they exist on some weird boundary between wave and particle, and that real matter would behave differently. Electrons are real matter. They have mass. They have charge. They are the particles that make up the outer shells of every atom in your body. And they went through both slits. Wave-particle duality was not a quirk of light. It was a feature of everything. The question physicists started asking next was obvious. If electrons do it, what about larger things? What about atoms? What about molecules? What about something you could almost see? The answer to that question took until the end of the 20th century to test properly, and the results were genuinely startling. The question sat in physics for decades. Electrons show quantum behavior. Atoms show quantum behavior. But atoms are still fantastically small. Where does the quantum world end and the classical world begin? Everything you see and touch is made of atoms. Your hand, this planet, a grain of sand, all quantum particles at the base level, and yet none of them show interference effects. You do not walk through two doorways at once. A baseball does not build up a wave pattern when thrown at a fence. The quantum rules vanish somewhere between the scale of electrons and the scale of objects you can hold. Finding where that transition happens became one of the central experimental challenges of modern physics. The first serious step came in 1999 when a team of physicists in Vienna, led by Anton Zeilinger, fired Buckminster fullerene molecules through a diffraction grating. Buckminster fullerene is a molecule made of 60 carbon atoms arranged in a perfect sphere, like a tiny soccer ball, about 1 nanometer across. It is roughly 1,000,000 times heavier than an electron. The experiment produced an interference pattern. 60 atoms, all locked together in a rigid sphere, traveling as one object, had shown quantum wave behavior. The molecules were going through multiple paths simultaneously, interfering with themselves and landing in the stripes and gaps pattern that is the hallmark of wave mechanics. The result drew attention from across the scientific community. But Zeilinger's team did not stop there. They kept scaling up. Each new experiment used larger and more complex molecules. Dozens of atoms became hundreds. Hundreds became thousands. The team built more sophisticated apparatus to handle the increasing mass and complexity of the objects being tested. Larger molecules move slower and have longer wavelengths, which requires wider slit separations and longer travel distances to produce a detectable pattern. The engineering challenges were significant. At every step, the interference pattern appeared. Molecule after molecule, regardless of mass or complexity, showed quantum wave behavior when the experiment was designed carefully and know which path information was allowed to exist. The boundary between quantum and classical was proving much harder to find than expected. Each successful experiment pushed the question forward. If molecules of a few hundred atoms could do it, what about a few thousand? What about something you could theoretically see under a microscope? The team developed new molecular species designed specifically for quantum interference tests. These were not naturally occurring molecules. They were custom-built, engineered to be as large as possible, while remaining stable enough to survive the experimental conditions. By the time the team reached the experiments that would make international headlines, the molecules they were using looked nothing like atoms in a textbook. They were elaborate, cage-like structures, visible proof that quantum mechanics could operate at a scale that was beginning to feel almost tangible. And the result was the same as always. The interference pattern appeared, the stripes were there, the math matched. Something that a chemist would call a large organic molecule was going through 2 openings at the same time. The universe had not drawn the line yet, and the experiment that finally tested just how far that line could be pushed came in 2019. What they fired through the slits that year would have seemed impossible to any physicist from the 20th century. The molecule had a name, but the name matters less than the size. 2,000 atoms, bound together into one enormous, intricate structure. A molecular cage, roughly 5 nanometers wide, which sounds small, but compared to an electron, it is colossal. It weighed more than 25,000 atomic mass units, making it one of the heaviest objects ever tested for quantum behavior. Picture the difference between a marble and a school bus, then compress that ratio down to the atomic scale. That is roughly the size jump from an electron to this molecule. The team in Vienna had been building toward this experiment for 2 decades. Each previous result had pushed the boundary a little further. Now they were firing something that strained every part of the experimental apparatus. To get interference fringes with an object this heavy, the slits had to be spaced at exactly the right distance. The molecule had to travel slowly enough that its wavelength was long enough to produce a detectable pattern. Slower travel meant more time in flight, which meant more time for the molecule to collide with stray gas atoms in the chamber. The chamber had to be evacuated to pressures approaching the vacuum of outer space. The molecule also had to survive the journey without breaking apart or absorbing heat from the environment, because any thermal interaction with surrounding matter would count as a form of observation. It would leave a trace of the molecule's position in the environment, collapsing the wave function before the molecule ever reached the detector. The team solved each problem methodically and ran the experiment. The interference pattern appeared. 2,000 atoms, all moving together as one quantum object, had traveled through multiple paths at once, interfered with themselves, and landed in the precise distribution that quantum wave mechanics predicted. The stripes were there, faint but unambiguous, matching the theory to within experimental error. This result was covered by physics journals around the world and earned Zeilinger a share of the Nobel Prize in Physics in 2022. What it proved, concretely, was that the quantum to classical transition is not at the scale of a few dozen atoms. The universe does not stop running quantum rules at any molecular size tested so far. The wave function of an enormous, complex object can survive long enough to produce interference, as long as the environment is kept from interacting with it. This finding has direct implications for a concept called quantum computing. Quantum computers work by keeping particles in superposition long enough to perform calculations that classical computers cannot. The same fragility that makes large molecule interference so hard to observe is the central engineering challenge of quantum hardware. Controlling the environment precisely enough that the wave function survives is the core problem. Every new size record in quantum interference experiments is also a data point for quantum engineers trying to build systems that can maintain superposition in increasingly complex objects. But the 2019 result also deepened the mystery. If quantum behavior can persist in objects made of 2,000 atoms, what is stopping it from persisting in objects made of 2 billion, 2 trillion? One concept in physics offers an answer, and it involves the environment itself becoming the observer. Your coffee mug is not in a superposition of positions right now. At least, it does not appear to be. You set it on the table, you walk away, you come back, and it is exactly where you left it. It has not spread into a probability cloud. It has not built up interference fringes on the wall behind it. It behaves exactly the way a classical object should. But the mug is made of atoms. Every atom in the mug obeys the rules of quantum mechanics. Every electron in every atom exists in a quantum state. The mug is, at its foundation, a quantum object. So why does it not act like one? The standard answer physicists give today is decoherence. Decoherence is what happens when a quantum system interacts with its environment. Every interaction carries information. When a molecule in your mug bounces off an air molecule, that air molecule now carries a tiny record of the mug's position. When a photon from the lamp above you reflects off the mug's surface, that photon carries a record of where the surface was. The mug is constantly interacting with its environment, and every interaction is a tiny measurement. Billions of these interactions happen every second. Each one is a small collapse. Each one injects a small piece of which path information into the surrounding environment. Collectively, they destroy the quantum coherence of the mug's wave function almost instantaneously, faster than any human instrument could detect. The mug cannot maintain superposition because it is being observed in the quantum mechanical sense by everything around it. The air, the light, the table beneath it, the heat radiating from its surface. All of these count as environmental measurement. All of them collapse the wave function continuously and completely. The time it takes for an object's quantum coherence to collapse from decoherence is called the decoherence time. For a single electron in a vacuum, the decoherence time can be very long. For a large molecule in air, it is a tiny fraction of a second. For a coffee mug at room temperature, the decoherence time is so short that no technology could ever measure it. It is effectively zero. This is why the 2019 experiment had to be performed in an extreme vacuum. Removing air dramatically extended the decoherence time of the large molecules, giving them long enough to travel from slit to screen while still maintaining their quantum coherence. Decoherence explains why the classical world looks classical. Large objects interact with too many environmental particles too quickly for quantum effects to survive. The interference patterns wash out before they can form. But decoherence is not the same as wave function collapse. Decoherence is a real physical process that can be described mathematically. It explains why quantum effects become undetectable in large systems. But it does not resolve the measurement problem. It does not explain why a single definite outcome emerges from a quantum superposition. It explains why the superposition becomes invisible. The question of what it actually is, and whether the other branches still exist somewhere, is still unanswered. Decoherence is one of the most important tools in modern quantum physics, and it leaves the deepest question completely open. But something even stranger was waiting at the edges of this framework. If decoherence is caused by environmental interaction, and if particles made of antimatter obey the same quantum rules, what happens when you send the mirror image of matter through the double slit? Decoherence does not just explain coffee mugs. It explains why you exist as a classical person in a classical world, despite being built entirely from quantum particles. Every atom in your body is in quantum superposition at some level. Every electron orbiting every nucleus exists in a spread-out quantum state, described by a wave function with a shape determined by the energy levels of the atom. And yet your body does not exist in a superposition of positions. You do not spread out across a room. You do not interfere with yourself when you walk through a doorway. The reason is scale and interaction density. Your body contains roughly 7 billion atoms. 7 followed by 27 zeros. Every single one is constantly interacting with its neighbors through electromagnetic forces. Every interaction is an exchange of quantum information. Every exchange is a tiny measurement that collapses a tiny piece of superposition into a definite state. The rate of these interactions is astronomical. The decoherence time of your body, the time it would take for your quantum coherence to survive long enough to produce any measurable quantum effect, is so short that it cannot be written as a meaningful number in human terms. It is many orders of magnitude shorter than the shortest events physicists can currently measure. For all practical purposes, you are always already collapsed. The environment around you has been continuously measuring you since before you were born. This is why cats are not in superpositions of alive and dead. Schrödinger's cat thought experiment assumed that the cat could be treated as a quantum system in isolation. A real cat is a macroscopic object immersed in an environment of quadrillions of photons, air molecules, and thermal vibrations, all interacting with it at every instant. The cat's wave function decoheres in an immeasurably short time. It has a definite state essentially instantaneously. The sealed box in Schrödinger's scenario cannot actually isolate the cat from decoherence. The box itself, the air inside, the walls, the litter of radioactive material, all of it creates an environment dense enough to collapse quantum superpositions on timescales far shorter than any observation delay. But here is the subtle and critical point. Decoherence suppresses superpositions. It does not eliminate them from the mathematics. The Schrödinger equation, applied to the full system of cat plus environment plus box, still produces a wave function that contains all possible outcomes. Decoherence makes the interference terms between those outcomes vanishingly small, but in the many worlds picture, those outcomes still all exist in separate branches. In the Copenhagen picture, decoherence is the mechanism by which the environment performs continuous measurement, collapsing the wave function into one definite outcome. In both cases, decoherence is the bridge between the quantum world and the classical world we experience. It is the reason why quantum computers are so hard to build. You are trying to create a system that is large enough to be useful but small and isolated enough to resist decoherence long enough to perform a calculation. The battle between quantum coherence and environmental decoherence plays out in every quantum device ever built. And physicists discovered that this battle plays out identically in matter and its opposite. Antimatter sounds like science fiction. It is not. Every particle of matter has a corresponding antimatter twin with the same mass but opposite charge. The antiparticle of the electron is called the positron. The antiparticle of the proton is called the antiproton. When a matter particle and its antimatter counterpart meet, they annihilate each other in a burst of pure energy. Antimatter is produced in particle accelerators routinely. It is also created naturally in certain types of radioactive decay and in lightning strikes. Positrons are produced in the human body by some medical imaging processes. This is not exotic. Antimatter is real, common at the particle level, and well understood. But the question of how antimatter behaves in the double-slit experiment had a surprising answer. Physicists ran versions of the experiment using positrons, the antimatter electrons, and antiprotons. Each time, the antimatter particles produced interference fringes on the detection screen, the same bright and dark stripes, the same mathematical pattern, the same dependence on which path information, and the presence or absence of detectors. Antimatter particles, like their matter counterparts, exist in superposition. They travel as probability waves through multiple paths at once. They interfere with themselves. They collapse into single points upon detection. The laws of quantum mechanics apply identically to matter and antimatter. This is both reassuring and puzzling. Reassuring because it confirms that the deep structure of quantum mechanics applies universally, not just to the particles we are made of. Puzzling because of a major open problem in physics called the matter-antimatter asymmetry. When energy converts into matter, which happens in the early universe and in particle accelerators, it produces equal amounts of matter and antimatter. The two should annihilate each other completely, leaving nothing but pure energy. And yet, the universe is made almost entirely of matter. Galaxies, stars, planets, and people are matter. Antimatter is vanishingly rare in the natural universe. Something in the early moments after the Big Bang caused matter to win. More matter was produced than antimatter by a tiny fraction, roughly one extra matter particle for every billion matter-antimatter pairs. That tiny excess survived the mutual annihilation and became everything that exists. The double-slit result with antimatter is clean. Same wave behavior, same observer effect, same collapse. But the deeper asymmetry between matter and antimatter in the large-scale universe remains one of the biggest unsolved problems in physics. For the double-slit experiment specifically, the antimatter result carries one important message. The quantum mechanical rules are not a property of matter alone. They are a property of the universe at a fundamental level, independent of which type of particle is being tested, which raises a fascinating new question. If the rules apply to matter in space, do they apply to the dimension of time itself? That question got its answer in 2023, and the experiment that answered it used one of the most familiar materials on the planet. For over 200 years, the double-slit experiment worked by splitting a wave in space. Two openings in a barrier, separated by a physical distance. The wave passes through both, crosses over in the gap between barrier and screen, and interferes. In 2023, a team of physicists at Imperial College London turned that geometry inside out. They removed the spatial slits entirely. No physical barrier, no holes in a wall. Instead, they created slits in time. The idea behind temporal slits comes from a theoretical concept called a time-varying medium. If you change the properties of a material very rapidly, you can create a moment in time during which light behaves differently than it does in the instants before and after. A brief window in time where light can pass versus reflect. If you create two such windows, separated not by distance but by a gap in time, you have a temporal double slit. The team built this using a thin film of indium tin oxide, a material widely used in industry for its unusual optical properties. When you hit this material with a powerful infrared pulse, you can temporarily change how it responds to light. For a brief moment, its reflectivity drops, then bounces back. The windows in time that the team created were extraordinarily short. Each one lasted only a few femtoseconds. A femtosecond is 1/400,000th of a second. Light travels about the width of a human hair in 1 femtosecond. These were not slow events. They were among the fastest controlled optical events ever performed. The team fired a pulse of infrared laser light at the treated film, while triggering two of these temporal windows in rapid succession. The light encountered the film twice, at two different moments in time, during windows when the film's reflective properties had changed. The light waves from both interactions then overlapped and interfered with each other. The result was an interference pattern, clear, measurable, and matching the mathematical predictions for a double-slit experiment run in the time domain rather than the spatial domain. The implications are significant. The double-slit experiment in space involves a wave split across two locations. The double-slit experiment in time involves a wave split across two moments. The interference principle operates across both. The underlying physics does not care whether the two paths are separated by distance or by duration. This confirms a deep symmetry in electromagnetism between space and time that physicists had predicted theoretically but never demonstrated this directly in a laboratory. The experiment also opened up a new set of tools for manipulating light. By varying the temporal properties of a medium, physicists can potentially control the frequency, color, and energy of light pulses in ways that spatial structures cannot achieve. But the most striking detail about this experiment was not the physics, it was the material. To understand what the Imperial College team actually built, you need to understand what happens inside indium tin oxide when a powerful laser pulse hits it. Indium tin oxide is a transparent conducting material. It lets visible light pass through while also conducting electricity across its surface. This combination of properties makes it extremely useful for touchscreens, solar panels, and anti-fog coatings on aircraft windows. It is one of the most manufactured thin film materials in the world. At the quantum level, indium tin oxide has a specific property that the Imperial College team exploited. When you hit it with an intense infrared pulse, the pulse excites electrons inside the material into higher energy states. For a very brief window of time, the material's optical response changes dramatically. Its refractive index, the number that describes how it bends and reflects light, shifts rapidly. During this window, the material reflects light differently than it normally does. Then the excited electrons lose their energy, the material returns to its ground state, and the optical properties snap back to normal. The entire event lasts only a few femtoseconds. The team precisely timed two such pulses to create two distinct windows of altered reflectivity separated by a controlled gap. Those two windows were the temporal slits. A probe pulse of laser light was then sent at the film during and around these two windows. The portions of the probe that arrived during the first temporal slit interacted with the altered material in one way. The portions that arrived during the second slit interacted in a slightly different way, because the gap between the two windows introduced a small time delay. When these two portions of the probe recombined after reflecting off the film, they carried the signature of having passed through two different temporal conditions. They interfered, and the interference was detectable as a change in the frequency distribution of the light. Instead of an interference pattern spread across a screen in space, the pattern appeared as a spread of frequencies, different colors of light distributed in a precise mathematical pattern. A bright stripe in the spatial version is a location where waves reinforced each other. The equivalent in the temporal version is a frequency where the waves reinforced each other. A dark stripe spatially corresponds to a frequency that was cancelled out by destructive temporal interference. The measurement required extremely sensitive spectroscopic equipment to resolve because the changes in frequency were subtle and the temporal windows were so short that isolating the effect from background noise demanded precision engineering. But the signal was unambiguous. A 200-year-old experiment, redesigned from scratch to operate entirely in the time domain, produced the same fundamental result. Waves interfere. Whether you separate the paths in space or in time, the principle holds. This placed the double-slit experiment in an entirely new conceptual category. It was no longer just a test of how waves behave in space. It became a window into how waves behave in the structure of space-time itself. And the material that made it possible is in your pocket right now. The spatial double-slit experiment changes where light lands. The temporal double-slit experiment changes what color light becomes. This distinction matters more than it might sound. In the spatial version, a wave passing through two slits spreads out and crosses itself. The crossing produces alternating bright and dark bands on a screen. The difference between a bright band and a dark band is location. The light arrives at different positions. Its color, its frequency, its energy per photon, all of these stay the same. What changes is the angle of arrival. In the temporal version, the wave does not split in space. It passes through two windows of time. The two portions of the wave are separated by duration rather than distance. When they recombine, the interference plays out differently. The result is not a pattern of bright and dark bands on a screen. The result is a pattern of amplified and suppressed frequencies in the light itself. Some frequencies come out of the interaction louder than they went in. Others are nearly silenced. The output spectrum, the spread of frequencies present in the light, has peaks and valleys arranged in a pattern that exactly mirrors the bright and dark stripes of the spatial experiment. This is a form of interference that creates new frequencies of light. The temporal slits do not just redirect light, they change it. Photons exit the interaction at different energies than they entered. The material, by switching its properties on and off in rapid succession, has acted like a time domain grating, a structure that sorts and redistributes light by frequency. This has practical applications that physicists and engineers are only beginning to explore. In the spatial domain, diffraction gratings are used everywhere. Spectrometers use them to analyze the chemical composition of stars, the purity of materials in a pharmaceutical lab, and the wavelengths produced by lasers. A temporal grating, in principle, could perform similar operations, but with properties that a spatial grating cannot achieve. For example, spatial gratings cannot change the frequency of light, only redirect it. Temporal gratings can. This makes them potentially useful for applications like optical signal processing, where you want to shift the frequency of a light-based signal without absorbing and re-emitting it. Converting signals from one optical frequency band to another could be valuable in high-speed communications and quantum networking. The 2023 experiment was a demonstration of principle rather than a practical device. The indium tin oxide film was small, the effect was subtle, and extracting the signal required significant processing. But the principle it demonstrated is solid. Light, passing through time instead of space, produces interference. The rules of wave physics apply across both dimensions. The universe handles time-separated paths and space-separated paths by the same underlying mathematics, and the material that created the first temporal slit in history is currently sitting in the glass panel of every smartphone that has ever existed. Indium tin oxide is invisible, literally. It is a transparent material, which is the entire reason it works in touchscreens. You cannot see it with the naked eye, but your finger interacts with it every time you tap a screen. The material conducts electricity while remaining transparent, which makes it the ideal coating for touch-sensitive displays. Sensors in the screen measure tiny changes in its electrical properties when your finger makes contact. Those changes are read by the device's processor as a tap or swipe. The conductive, transparent layer sitting between your finger and the pixels is, in essentially every modern touchscreen device on the planet, made of indium tin oxide, the same compound, the same optical and electrical behavior that the Imperial College team exploited to create temporal slits. The material that produced the first interference pattern in the time domain is a substance that collectively billions of people interact with billions of times every day without knowing its name. The connection is more than symbolic. It illustrates a consistent pattern in the history of quantum physics. The discoveries that seem most abstract and most remote from human experience consistently turn out to underlie the most useful and most common technologies. The understanding of quantum energy levels in atoms led directly to the laser. Lasers now read data from every disk drive, perform surgery, cut metal in manufacturing plants, and transmit data through fiber optic cables under the ocean at the speed of light. The understanding of quantum tunneling, where particles pass through barriers they classically should not be able to cross, led directly to the transistor. Transistors are the basic unit of every microchip ever made. The phone in your pocket contains tens of billions of them. The understanding of quantum spin states led to magnetic resonance imaging. Hospitals around the world use this every day to image the human body without radiation. Each of these technologies began with a baffling experimental result in a physics laboratory, a result that seemed purely theoretical, a result that raised more questions than it answered. The temporal slit experiment is very early in that chain. It demonstrated a principle. The engineering applications are speculative at this stage. But the principle is real and confirmed, and the history of quantum mechanics strongly suggests that confirmed principles have a way of becoming indispensable technologies within a generation or two. The double slit experiment has been running for 200 years, and every decade it opens a new door. The door it is currently opening leads somewhere that makes physicists genuinely uncomfortable, because it connects the most precise experimental result in science to the deepest question in philosophy. Does the universe only exist because something is looking at it? The observer effect has a metaphor that some physicists and philosophers find uncomfortably precise. A video game does not render what is off-screen. When you play a game and walk down a hallway, the walls you cannot see are not being drawn. The processor only calculates what is in the camera's view. The moment you turn around, the engine instantly generates whatever should be visible. From the perspective of a character inside the game, reality appears fully present everywhere. But from the perspective of the hardware running it, only the observed portions exist in any meaningful sense. The double slit experiment, read literally, describes something similar. A photon, unobserved, exists as a wave of probabilities spread across space. When something interacts with it, a definite position appears. When nothing interacts with it, no position exists. Reality at the quantum level is genuinely absent until observation creates it. A small number of physicists and philosophers, most prominently Nick Bostrom and later Max Tegmark, have used this as part of an argument that the universe might operate according to computational logic. If the deepest layer of physical reality consists of information, and if observation is what converts probabilistic information into definite states, then the structure of quantum mechanics looks less like a classical physical universe and more like a universe that runs on something like logic and code. This is the simulation hypothesis applied to quantum mechanics. The idea is that the observer effect is not mysterious at all, once you accept that reality is informational rather than physical. A simulated universe would naturally produce exactly this result: systems in superposition until queried, definite outcomes only when the processor needs to produce them, and a mathematical framework that perfectly describes probabilities but never gives you a picture of what is happening when no one is looking, because nothing is happening when no one is looking. It is important to be clear about what this is. It is a philosophical interpretation, not a tested scientific theory. The simulation hypothesis makes no predictions that differ from standard quantum mechanics. You cannot design an experiment that distinguishes between a physical universe with observer-dependent reality and a simulated universe with observer-dependent reality. The two frameworks are empirically identical. Most physicists treat the simulation hypothesis as an interesting thought experiment with no scientific traction. Some consider it a category error, confusing a metaphor for a mechanism. But the observer effect itself is real, confirmed, and has no classical explanation. Something about the existence of information changes the physical behavior of particles, whether that means the universe is a simulation, or that measurement creates reality in some deeper ontological sense, or that the Copenhagen interpretation is simply the most accurate description we have, remains genuinely open. The double slit experiment does not prove the universe is a simulation. What it proves is that reality at the quantum level is deeply, irreducibly connected to the act of observation, and the nature of that connection is still not understood. The practical consequences of that connection, however, are arriving fast. The double-slit experiment is not just a philosophical puzzle. It is the operating manual for an entirely new class of technology. Quantum computing works by using superposition. A classical computer stores information as bits, each one either 0 or 1. A quantum computer stores information as quantum bits, called qubits, which can exist in superposition, being 0 and 1 simultaneously until measured. A single qubit in superposition represents 2 states at once. 2 qubits represent 4. 10 qubits represent 1024. 50 qubits represent more states simultaneously than there are atoms in your body. Because quantum computers can process all those states in parallel, they can solve certain categories of problems exponentially faster than any classical machine, simulating complex molecules for drug discovery, optimizing supply chains with millions of variables, breaking encryption codes that would take classical computers longer than the age of the universe to crack. The challenge is decoherence. Qubits are quantum systems. They need to maintain superposition long enough to complete a calculation. But they are physical objects in a physical environment, and as we know from the double-slit experiment, any interaction with the environment collapses quantum states. Engineering systems cold enough and isolated enough to preserve coherence for useful computation is the central technical problem in the field. Quantum encryption uses a different feature of quantum mechanics. Because measuring a quantum state changes it, you can send a secret key encoded in the quantum states of photons and detect whether anyone intercepted it. An eavesdropper would have to measure the photons, which would disturb them in a detectable way. The recipient would see the disturbance and know the key had been compromised. This is called quantum key distribution, and it is already used in some secure government and financial communications. Quantum sensing uses the extreme sensitivity of quantum systems to environmental disturbance, the very fragility that makes quantum computers hard to build, as an advantage instead. A quantum sensor can detect gravitational variations, magnetic field changes, and time intervals with precision far beyond any classical instrument. Applications include navigation systems that work without any satellite signal, medical imaging with higher resolution than anything currently available, and geological surveys that can detect underground structures by measuring tiny variations in local gravity. All of these technologies grow directly from the principles demonstrated in the double-slit experiment: superposition, interference, the collapse of wave functions by measurement, the entanglement of particles across space. These are the fundamental resources of quantum technology, and they were all first revealed, or later illustrated, by variations of the experiment Thomas Young performed with a pair of scissors and a sunbeam in 1801. The gap between that first demonstration and the current technology is exactly what the history of quantum mechanics looks like. Abstract result, decades of confusion, theory built on theory, then application. The final unresolved piece sitting at the center of all of it is the question that 200 years of experiments have not answered. The question that makes the whole thing uncomfortable in a way that math alone cannot dissolve. What exactly is an observer, and does it have to be alive? 200 years of experiments, photons, electrons, molecules of 2,000 atoms, antimatter, slits in space and slits in time. Every test confirms the same thing. Observation changes what particles do. The act of gathering information collapses superposition into a single definite outcome, and the field of physics still does not have a complete answer to the most basic question the experiment raises: what counts as an observation? The working answer in mainstream physics is any physical interaction that encodes which path information in the environment: a detector clicking, a photon scattering off a surface, an electron entangling with another particle. None of these require a brain. None require a living organism. The mathematics of decoherence handles it entirely mechanically, and most physicists are satisfied with that. But a minority of physicists have never found that answer complete. and their concern goes to something the formalism leaves unaddressed. In the standard framework, observation collapses the wave function. But what physically performs the collapse? Decoherence spreads the superposition into the environment but does not collapse it in the Copenhagen sense. The Schrödinger equation, applied to the entire system, including the detector and the environment, still produces a wave function containing all outcomes. The collapse is either an additional rule bolted onto the theory, an aspect of branching that we only perceive as collapse, or something else entirely. A small but serious group of researchers, including Eugene Wigner in the mid-20th century, and more recently physicist Roger Penrose, have proposed that consciousness plays a role that standard quantum mechanics does not account for. Wigner designed a thought experiment called Wigner's Friend, in which an experimenter performs a quantum measurement inside a sealed lab. From inside the lab, the measurement has occurred and the wave function has collapsed. From outside the lab, according to the mathematics, the entire system, lab, experimenter, result, is still in superposition until the outside observer checks. If the collapse is truly triggered by physical interaction alone, then the outside perspective and the inside perspective should be reconcilable in a consistent physical picture. Recent experimental tests of an extended version of Wigner's Friend using pairs of entangled photons and two independent observers have produced results that some physicists interpret as showing the two perspectives cannot always be made consistent, a result with implications for whether observation is purely physical or involves something additional. These experiments are contested, the interpretations are disputed, the conclusions are not settled. Penrose has proposed that wave function collapse is caused by a threshold of quantum superposition in spacetime itself, a gravitational instability that triggers a definite outcome once the mass-energy difference between superposed states becomes large enough. In this view, collapse is a real physical process driven by gravity, and consciousness is relevant only because neurons may use quantum processes that involve this gravitational collapse. These ideas are speculative and remain outside mainstream physics, but they have not been falsified either. What the double slit experiment leaves us with, after every version of it ever run, is a confirmed fact and an open mystery. The confirmed fact is that the quantum world is inseparably connected to observation. The open mystery is what observation ultimately is. Thomas Young cut two slits in a blind and watched light do something impossible. 200 years later, the physics community has built the most precise, predictive framework in the history of science on top of that result. And the question of what is really happening, what reality is doing when nothing is watching, remains exactly as open as it was when the first stripe appeared on that card in a dark room in 1801. The universe keeps the answer just out of reach, and every experiment we design to catch it only makes the question deeper.